This is the video for assignment number 6 and unit number 9 on arithmetic and geometric sequences and series. And we are now, it is now time for us to talk about geometric series. We've been spending a couple days on arithmetic series and how to add those numbers together. The difference here is that a geometric series is kind of like a geometric sequence in that there isn't a common difference. Remember that in a geometric sequence there's a common ratio. So for example, in this particular example, we start with the number 1, we multiply by 2, we multiply by 2 again, and by 2 again, and by 2 again. We do that 20 times, we'll end up with 524,288. But the whole purpose now is not just to find a particular term in a sequence, but to find the entire sum of the series. So there's a few things that right off the bat that we can talk about, and that is how can we write this in summation notation. So we should be pretty familiar with that. Summation notation, we're going to start with the lower limit of 1, and we're going to go to the 20th term. And if you remember correctly, that this formula is always an explicit formula. And so the explicit formula for a geometric sequence is going to be the first term, which in our case is 1, but then we're going to multiply it times a common ratio, which in this case is 2, to the n minus 1 degree, or n minus 1 power. And so that's how we would write this in summation notation. So questions can be asked in either form. They can be written like this, or they can be written like this, but they mean the same thing. So then the question is, how in the world do we find the sum of these numbers? So we want to find the sum of all of those numbers, but it's not like an arithmetic one where we can take the first term plus the last term. If I add 524,288 plus 1, I get 524,289. But then if I add the next biggest and next lowest, I don't get the same number. So the formula that we had that worked for arithmetic series is not going to work for a geometric series. So that means we're going to have to come up with a formula that really does work. And so I want you to follow along here because I'm going to write and we're going to develop this formula. It's kind of a more difficult one to follow than the way we developed the arithmetic one. And I want to see if you can follow along here. We're going to start with S of n. This is for a geometric series. And let's just write out what the series would look like. We'd have the first term plus the second term plus the third term. And we would keep adding all the way up until we get the last term of the sequence, of the series. And so we could be more specific here. We know that the first term is a sub 1. We know that the second term can actually be written like this, a sub 1 times r, times the ratio. For example, in this particular example, the second term here is the number 1, which is the first term, times 2. The third term is the first term times the ratio squared. Because the third term is 4, but I could find it by starting with 1 and multiplying it times the ratio twice. And I can do that with all of these terms until the very last term, which is a sub 1. That should be a sub 1, not n. A sub 1 times the ratio n minus 1 number of times. And that's just a 1. All right. So what I'm going to do now, there's going to be a reason for this, but I want to take all of these terms and just multiply both sides of this equation by r, by the ratio. So if I did that, this side would just be r times s sub n. Should have put it down here. Then I'm going to multiply each one of these terms by r. So this is going to be a sub 1 times r. The second term, which was a sub 1 times r, is now going to be a sub 1 times r squared. The third term is a sub 1 times r squared, but now if I multiply that times r, it's going to be times r to the third. And I can keep going here, keep adding these together, but now this term is going to be a sub 1 times not r to the n minus 1, but just r to the nth power. All of these, like this was the first degree, this is now the second. This was the second degree, it's now the third. So it's always 1 more than that. And 1 more than n minus 1 is just n. The reason I did that is because I want to take these two equations and subtract them from each other. Now, if we were doing this in class, now would be about the time when somebody would say, who did this for the first time? I wish I knew the answer to that question. They're a lot smarter than me. So here's what I'm going to do. I'm going to subtract these. This is like 1 times S. I can just write it like this. This side of the equation is going to be S sub n minus R times S sub n. And so the other side of the equation, if you look here, when I subtract these, a sub 1 times r minus this term, those are going to cancel out. A sub 1r squared minus this a sub 1r squared, those are going to cancel out. And we're going to have a bunch of terms that cancel out. And what we're going to have left is a sub 1 and then minus a sub 1 times r to the nth power. So now what I want to do is factor something out of here. Like, for example, out of this side of the equation, I can factor out an s sub n. And what I'll have left in the parentheses is 1 minus r. They just both have an s sub n in common. So if I pull an s sub n out, s sub n times 1 is s sub n. S sub n times r, negative r, is negative r s sub n. And if I do the same thing here, if I pull out what they have in common, actually, this should be a sub 1 here, because it came from here. If I pull out what they have in common, they both have an a sub 1. So inside the parentheses, then I'm going to have 1 minus r sub n, or r to the nth power. A sub 1 times 1 is a sub 1, and a sub 1 times negative r to the nth is negative a sub 1 r to the nth. So I just pulled out what they have in common. But now I can solve for s sub n. In other words, if I divide both sides by 1 minus r, these cancel, and the sum of all of the terms, which is what I started with, instead of being written like this, can now be written as a sub 1 times 1 minus r to the nth power over 1 minus r. This is now a very usable formula that we can use in order to find the sum of all of our, at least our finite, that means one that has a beginning and an end, all of our finite geometric series, which is the type of series we're going to be talking about in this lesson. So let's transfer this formula up here. Again, s sub n is going to equal a sub 1 times 1 minus r to the nth power over 1 minus r. Now, I will not ask you on a quiz or a test to develop this formula, but I do want you to understand why it works, and that's why I wanted to go through. I just didn't want to say, here's a formula that works, and have you have no idea about why it works the way that it does. So now let's use this formula to find the sum of these numbers. The sum is going to equal the first term, which in our case, the first term is simply 1. We're going to multiply that times 1 minus the ratio. In this case, I'm doubling it each time. So it's 1 minus 2 to the nth power. The nth power is how many terms I'm going to have. In this case, I have 20 terms over 1 minus the ratio, which is 1 minus 2. And if we develop that formula, we're going to have 1 minus, this is 1,048,575 over negative 1. And that simply comes out to 1,048,575. And the sum of those terms in that geometric sequence is 1,048,575. All right, so let's use this on a more practical example. Let's suppose that our example number 2 is, we want to find, you can put down example number 2, we want to find out how many Homestead High School graduates are there in the world. How many Homestead High School graduates are there in the world? So a bit of a history lesson. This is not completely accurate, but it's pretty close. Homestead High School was opened in, and the first graduates graduated in 1978. I believe the doors were opened in 1977. And in 1978, I don't know exactly how many graduates there were that year, but we're going to assume that in that particular year there were 65 graduates from Homestead High School. And so we're going to assume that that is our first term. I didn't write this down again, so we're going to do it as we go. Then the following year, I want to know, let's just kind of develop this a little bit, how many graduates there were. We're also going to assume that the population of Homestead grew by 6% every year. So that means that in the year 1979, if we take 65 and we're going to multiply that times our common ratio, which our common ratio, if it's an increase of 6%, is going to be 1.06. And that means we'd have 68.9. We would round that to maybe 69 kids. 1980, if I start with 65 and I multiply it times 1.06, but this time it's to the second power because I would do it twice, it's going to be roughly 73. And I can continue that, but each time multiplying by 1.06 each time. Well, let's first figure out how many people will have graduated. Let's take the year 2014. How many people graduated in the year 2014? Well, if that's, and then we're going to add all these numbers together. 2014, I believe, is 36 years after 1978. So if you remember, our explicit formula is going to look something like this. It's always a sub n equals the first term, which is a sub 1, times the common ratio, n minus 1 number of times. So in this particular case, we want to find the 36th term. So the first term is 65, and we're going to multiply it times our common ratio, which is 1.06. And again, this is an estimate because these numbers have to be rounded to the nearest person. But then I'm going to take 36 minus 1, which is the 35th power. So if I take 1.06 and I raise that to the 35th power, and then I'm going to multiply that times 65, because that's how many people were there the first year. That means in the year 2014, there had to have been 499 graduates from Homestead High School, which is pretty close. We're a little over 2,200, 2,300 kids. So in the year 2014, we can assume that there was roughly close to 500 students that graduated. And actually, if I rounded that correctly, it would be 500 exactly. But technically, we don't really need to know the last term. What I need to know in order to find the sum of all of these numbers is I need to know everything for this formula. The sum, messed up again. The sum of all of these terms is going to be a sub 1 times 1 minus the ratio to the nth power over 1 minus the ratio. So the first term, 1978, there were 65 students that graduated. That's going to be 1 minus our ratio, which is 1.06. We're going to raise that 1.06 to the nth power, which is the 36th power, over 1 minus the ratio, which is 1.06. And so if I do that correctly, I'm going to take, again, I should have done this ahead of time, but I'm going to take 1 minus 1.06 to the 36th power, and that gives me, it's going to be 65 times negative 7.147, and then 1 minus 1.06, that's negative 0.06. And so I'm going to take that negative 7.147, and it actually goes on a lot longer than that, but I'm going to multiply that times 65, and I'm going to divide it by negative 0.06. And what I get is 7,742 graduates of Homestead High School over its entire existence. So, And that would be how we find the sum of that geometric series. So let's take another example here, and this time I'm going to write the example a different way. So let's assume that you are graduating from college. This is example number 3. And just to write this out, let's say you are an accountant and you get a job as an accountant and you make $36,200 your first year, and your boss has said that you can pretty much count on a 4% raise every year. So let's assume that you stay in this job your entire career. You start the age, let's say 23, and you work until maybe 63, so that's 40 years. Just for fun, you go home that night before you accept the position and you want to find out, well, how much money would that be over my lifetime? So let's try to figure this out. We want to find the sum of all of these numbers. We could write this in summation notation simply by doing this. The first term to the 40th term, because I'm going to have 40 years. But my first year, I made $36,200. But I'm going to multiply that each year times my ratio. And if it's a 4% raise, that means my ratio is going to be 1.04. And it's to the n minus 1 power. This is the explicit formula. Using our summation formula that we have, it's a sub 1 times 1 minus r to the nth power over 1 minus r. So our first term, in this case, is 36,200. We're going to multiply that times 1 minus 1.04. I always draw that parenthesis before I put the exponent in there. I shouldn't do that. To the 40th power over 1 minus 1.04. And so now it's just a matter of calculating this. On our calculators, we would have 36,200. 1 minus 1.04 to the 40th power is negative 3.8. And if I take negative 3.8 and all those numbers after it, multiply it times 36,200, divided by, this would be negative 0.04, I would have a total of $3,439,923.67 that you would make during your career as an accountant. Compare that to Alex Rodriguez, who got paid $16 million for 1 year of baseball. That doesn't sound too hot. But if you compare it to a lot of other people, that's probably pretty good. So anyway, this is how you find the sum of finite geometric series, which is what our homework assignment is about. And hopefully you'll do well on your homework, and we will see you tomorrow in class.